So let's look at another 3-input Karnaugh map. And specifically in this example, we're going to notice an example of edge wrapping, or where we'll be able to utilize that. So let's get to it, right? Our Karnaugh map is 3 inputs, so it's going to be shaped like this. And we're going to have 8 cells, right? Because there's 8 rows in our truth table, 2 to the 3. And draw our little line here to divide our axes. We're going to have A here, B here, and C here, because we always start with our most significant bit and go down to our least here, so A, B, and C. And then we're going to label this. And remember, we're labeling this in gray code because only one bit changes as we count. So we have 0, 0, 0, 1, 1, 1, 1, 0. This order is super important. If you screw it up, it's pretty much going to toast you for the rest of the problem. So you want to make sure that you're always double checking that you're doing your axes in the proper order. And it's kind of difficult because we also just recently learned how to count in binary as well, and it's different in this order, so we kind of learned 2 different ways to count. But just remember, this is really only going to be used for Karnaugh maps. So now let's fill this one out going from the truth table to the Karnaugh map rather than the other way. So here we're going to look for a spot that A, B, and C are all zeros. So that's this cell here. Now A and B are zeros and C is a 1. That's this cell. The A is a 0, B is a 1, C is a 0. So A is a 0, B is a 1, C is a 0. And then you can actually start noticing that there's a bit of a flow to this that we can use. And so, oops, sorry, this shouldn't be a 1, this should be a 0. My bad. So we've got A's a 0, B's a 1, C's a 1, A's a 0, B's a 1, C's a 1. That's another 0. Now let's look where we have A's a 1, B's a 0, and C's a 0. That's right here. A's a 1, B's a 0, C's a 0. And then our next cell, A's a 1, B's a 0, C is a 1. It's right here. And we can actually conclude that the rest of these are just going to be zeros, just because that's these 2 here. So we've got our Karnaugh map filled in, and now we just need to circle our groups, or a proper term for them is implicants. And so there's 2 ways that this could be done. Well, there's more than 2 ways, but there's one way that you might immediately jump and say, oh, right here's a group, and right here's a group. But that's actually not as efficient as possible. This is still a proper way to do it, and we would get a function, but it wouldn't be the most simplified function. In fact, it's probably a good exercise that you try and do this and see what this function would look like, and then we'll look at a more simplified version and see if it is in fact more simplified. And what I'm alluding to is right here in our title, edge wrapping. So you can almost kind of think of, it's not going to be a super great drawing, but if we took this and wrapped it around a ball such that this edge was touching this edge and this edge was touching this edge. So you can kind of think of it, right? It's, well, it would kind of be cut like this, and then you would have your four divisions there. I know I've only got 3. And so this edge would wrap all the way around this edge is touching. It's a lot easier to visualize if you can actually do it in 3 dimensions. But anyway, so just take for granted that these edges are touching, and so are these ones. That means all these corners are actually touching in the same exact point, right? They share a vertex. So it turns out that this way of grouping things is wrong because remember, we want to have our groups or our implicants be as big as possible. If you want our implicants to be as big as possible, instead, what we could do is we could group. Oops, not a super good group there. We could group over the edge, and this is how we draw this if we're going over the edge. We just kind of cut it into two spots, and we know that we're actually circling these two and these two, or it's a group of 4. So that's the real implicant is that we want to use is this green guy. And let's look and see what variables are staying constant in this group. So we see that A is a 0 for this column, and A is a 1 here, so that means A changes. B stays as a constant 0, right? B stays as a constant 0 here, so we want to put B not. And then it looks like C changes, right? C is a 0 here, C is a 1 here, so C is not used. So this implicant is just B prime. And that's all of the ones, so that means that our end function is x equals B prime. So that's just another thing to be careful for when you're really trying to simplify your functions, is remember that your edges are touching and your implicants can wrap across here.